Ms. Chun with your day 12 homework. So we've come pretty far with these different stoichiometry skills. We're now sort of in the middle of applying multiple concepts involving the molarity equation, mixing solutions and double replacement reactions to form precipitates, and being able to analyze a scenario like that, applying not just what we know about converting between grams and moles and moles and moles and moles and grams, but also applying concepts involving limiting and excess reactants. And finally, with our most recent day 10 lab, we learned about a concept called percent yield. So here is a problem that's going to require multiple layers for you to basically apply everything that we've been talking about so far, but we'll break it down step by step. And then I think you'll start to see some old patterns emerge. We're just going to be connecting them now all into one big scenario. So let's look at the first piece of information we're given. We're dealing with a solution of calcium nitrate being mixed with another solution of potassium phosphate. So before we even engage with the numbers, I'm going to propose that we write out a balanced chemical equation. Since both of these have a volume and a molarity, we're going to assume that the calcium nitrate and the potassium phosphate are both aqueous solutions. And you can double check your solubility chart. You'll see that anything that combines with nitrate and anything that combines with group 1 ions are going to end up being soluble in water. So because we're given the molarity and volume of these two solutions, we can assume that we're starting out with two aqueous reactants. And then we can recognize this is going to be a double replacement reaction since both of these are ionic compounds. It helps us to list out the different ions that are involved with each compound. So we have a Ca2 plus cation, calcium's in the second column of the periodic table. Nitrate is a polyatomic. You can look on the polyatomic table for reference. It carries a -1 charge. The cation in potassium phosphate is potassium. Potassium's in the first column, so it forms a +1 charge. Phosphate is a polyatomic. On the table, you can see that it carries a 3- charge. So now we're in good shape because we can now predict the new combinations that'll form. We see that this calcium, Ca2 plus ion, will seek out the phosphate ion, and when they come together, we'll need 3 of these calciums to balance out 2 of these phosphates if we want the charge to balance out. So we're going to write it as Ca3 parentheses PO42. And our second product will involve this potassium pairing up with this nitrate. It's a +1 and a -1 charge, so we just need 1 of each ion to form KNO3. You'll look at your solubility table. You'll see that calcium phosphate is going to form an insoluble solid. That's going to be our precipitate. And then potassium nitrate will form an aqueous solution. So if we were to balance this out, let's see. I see that we have 3 calciums on the right side, so we're going to need a big 3 in the front here. That's going to lead us to having 6 nitrate ions on the left side, so we're going to need to put a big 6 in the front here. That means we're going to need 6 potassiums. We have 3, so 3 times 2. We're going to put a big 2 in front there. That'll give us 6 potassiums. That'll give us 2 phosphates, which we have on the right side as well, so that looks like it's balanced. So yay, we did the first step. We balanced and predicted the products for a double replacement reaction. Now let's kind of look at what the numbers are given to us. So it looks like we're given the milliliters and molarity for each of the reactants. So this is going to actually be helpful because we're going to be able to use the volume and the molarity to solve for the moles of each reactant. And then it's going to start to look like a limiting reactant type of scenario where we're going to have to figure out what the limiting reactant is. But let's see what our end goal is. We're trying to find the percent yield of the precipitate. So we just found out that calcium phosphate is our precipitate. And look at this piece of given information. We're given the grams of the precipitate that were actually produced in the lab. So someone actually carried out this experiment for us, and part of the given information is this little bit of info here that we know is going to be called the actual yield. And so our end goal is to find the percent yield of the calcium phosphate. So don't forget, percent yield is going to depend on two things. That's going to depend on how much of the product was actually made in the lab. And then it's also going to depend on something called the theoretical yield, which is how much of the product we're expecting to make. So in order to solve for percent yield, we were given the actual yield. Our job now is to find the theoretical yield. So that's what this fun stoichiometry is going to help us to get to. So let's resolve the given information up here first. Let's find the moles of each reactant, and then we'll go from there. So if we want to find the moles of calcium nitrate, we're going to have to take the molarity. To solve for the moles, we'd have to convert the milliliters to liters. So we're dealing with 0.0250 as our volume. We multiply those two numbers together. So I'm going to take the 0.115 and multiply it by the 0.0250. And we're going to end up with 0.0028, I'm going to round to 3 sig figs, 288 moles of calcium nitrate. And then I'm going to do the same thing, but with the given information for potassium phosphate. So I'm going to take the molarity, and that's going to equal the moles, which we'll solve for, over the volume, which again is going to be 0.0250 liters. So when I solve for the moles of potassium phosphate, I get 0.218 times 0.0250. We're going to keep 3 sig figs again, so it's going to be 0.00545 moles of potassium phosphate. So now that we know the moles of each reactant that we have to start off with, let's set up a mole to mole ratio to kind of figure out what our limiting reactant is. So I'm going to take our calculations over here towards the right side. I'm going to come up here. So I'm going to just choose the first reactant that was listed, the moles of calcium nitrate. So let's take the 0.00288 moles of calcium nitrate, and let's set up a mole to mole ratio between the moles of calcium nitrate and the moles of the other reactant, which is the potassium phosphate. We'll use the coefficients. So for every 3 moles of calcium nitrate that react, 2 moles of potassium phosphate will react. So we're finding out that if all of our 0.00288 moles of calcium nitrate react, we would need just about 0.00192 moles of potassium phosphate. This is how much we would need. And let's look back at our given information. This is how much we have. So if all of our calcium nitrate were to react, we would need 0.00192 moles of potassium phosphate. Do we have enough? We have 0.00545 moles of potassium phosphate. So we have more than enough potassium phosphate for all of the calcium nitrate to react. So therefore, our conclusion is that our limiting reactant must be calcium nitrate. Okay, so this is pretty important stuff, because now we know that we can go ahead and take the given amount of calcium nitrate and assume that all of it is going to react. So I'll take the 0.00288 moles of calcium nitrate once more and start off a calculation. This time we can go ahead and start to solve for what's going to help us to find the theoretical yield of the precipitate. So we agreed that the precipitate was calcium phosphate. So let's set up a mole to mole ratio between the moles of our limiting reactant, calcium nitrate, and the moles of what we're looking for, which is going to be calcium phosphate. So that's a 3-to-1 mole ratio. For every 3 moles of calcium nitrate that react, we can get 1 mole of our precipitate. So that's going to tell us to take the 0.00288 and divide it by 3. And we're going to get just about 0.000960. I'm going to keep 3 sig figs. That's how many moles of calcium phosphate I can expect to produce, assuming all of our limiting reactant it gets used up. So final step, since our actual yield was given in terms of grams, we need to convert this theoretical yield in terms of grams. So If you want to use scientific notation to handle all these zeros in the front, feel free. We're dealing with a pretty small scale reaction here. So we know that we're going to have to do a mole to gram conversion now for our calcium phosphate, which is the precipitate. So then we need to find the molar mass of calcium phosphate. Calcium has a molar mass of about 40. There's 3 of them. Phosphorus has a molar mass, I think, of about 31 or 32. And then oxygen has a molar mass of 16, but keep in mind there's 2 phosphorus atoms and 8 oxygen atoms. So that's fun. I'm going to add that together. And I may have rounded slightly differently than you, but I got just about 312 grams per mole. I may have been a little bit lazy there, but we're going to go with that molar mass, about 312 grams per mole, grams per 1 mole for the molar mass of calcium phosphate. And then I'm going to multiply that by the 0.000960. And then you should end up with just about, so I rounded kind of heavily, so you may have gotten a number that's slightly smaller than this, but just about 0.300 grams of calcium phosphate. So what you just found here, this is your theoretical yield. Okay, because we just found out the maximum amount of grams of calcium phosphate that we could expect to produce from this reaction if all of our starting amount of calcium nitrate reacted completely. But now we have to bring it back to what the question was actually asking for, which was the percent yield of the precipitate. Don't forget that the actual yield was already given in the problem. So this was the result of someone doing the lab and isolating the calcium phosphate. And they found that they were able to get 0.254 grams of the calcium phosphate isolated. So what we're going to do is to solve for percent yield, we're going to plug in the 0.254 grams directly into the top part of this equation, and we're going to divide it by our answer from doing all this lovely stoichiometry. And we're going to get some decimal number, which will convert to a percentage by multiplying by 100. So we can get 0.254, and we're going to divide it by just about 0.3. Like I said, I rounded kind of heavily, so you might actually end up with a theoretical yield that's a little bit lower than mine, but the process is the same. So I end up with a decimal that's about 0.847. If I multiply that by 100, I get it in terms of a percent, which is just about 84.7%. So that means out of the expected amount of calcium phosphate that we were hoping to get for this reaction, we actually only got 84.7% of that amount based off of whoever tried to do the lab for us. Okay? So there we go. That's a big summary of a lot of different skills. We will continue to practice this, but hopefully that gives you an example problem to work off of for the rest of our day 11 homework. I'm sorry, not day 11, day 12 homework. I'm mixing up the days. Okay, everyone, good luck.